Newton then was interested in the mathematics of motion, which later becomes called the calculus. And we're going to revisit this topic on motion later on in the second half of the class when we talk about the second half of calculus, integration. So the first half of the class is the derivative or the slope of a tangent line and learning all of the different ways that that fits. And again, we're going to look at a bunch of jumbled, disconnected ideas, but they're all connected by this idea of the derivative. And we're going to start off with the most important historically beginning points of the calculus. So we're going to talk about motion. And we're going to focus on what is called confusingly rectilinear motion, but you can call straight line motion. The reason why we're doing straight line motion is because it's less confusing. It's less complicated. It's a good entry point for using the derivative to do more than the stuff we've been doing. So we're going to start off with three really important ideas, and it's largely a vocabulary issue. So these are the three ideas. It didn't fit as well as I thought it would, sorry. But I'm going to give you some time to write all those down. Okay, let's recapitulate. We looked at a bunch of connected ideas, and I hope that whole time you were making connections. I tried to make some clearer and stand out to you, but it's definitely worth a look. And when you're like, how do I study for math? This is how you study for math. You go back through and maybe you write in additional things later. Things that maybe you said or thought the first time, but not the second time. Or I think I meant the reverse of that. Okay? So we've got position, velocity, and acceleration. Acceleration is the derivative of velocity, which is the derivative of position. Or acceleration is the second derivative of position and the first derivative of velocity. And the reason why we call those different things is because English is a funny language. Acceleration, we're going to take to understand is the change in velocity. Velocity, we're going to take to understand is the change in position. And we want to be very careful on distinguishing between instantaneous velocity and acceleration and average velocity and acceleration, as is spelled out later on. We are focusing right now on the x-axis, but honestly, we can go up and down, and up corresponds to right, down corresponds to left if we're moving along the y-axis. So we did a whole bunch of statements about position and things. So these apply universally. T equals 0 means at rest. T equals 2 would mean after 2 seconds. X of t equals 0 would mean you're at the origin. X of t equals 5 would mean you're 5 units to the right of the origin. But what I want to make sure you do with that is you don't associate starting position with 0. The starting position has time of 0. It doesn't have to start as 0, just like we talked about later. Then we have some ideas here about the velocity. So we talked about a sign of 0 means at rest, a sign of positive means you're moving right, a sign of negative means you're moving left. And we followed up with that by saying if you're changing direction, oops, that's later, sorry. I got all excited to think about changing direction. So to reinforce the thing I was saying before, average velocity is going to be average change in position. So if you're calculating average velocity, what you're going to want to do is do 2 velocity values. You don't want to do 2 velocity values, and I'll tell you another reason why, other than just the vocabulary reason. Think about units. If your position is measured in miles, your velocity is going to be measured in miles per hour, probably, okay? If you were to do a slope calculation like you would here with your velocity, you would have miles per hour in the numerator and hours in the denominator. So you'd have miles per hour, which are units for acceleration. So you want to be very careful with this, and remember that average velocity means change in position over change in time. So you want position values. And if you're doing average acceleration, change in velocity over change in position. And we're doubling down on that idea. Again, instantaneous velocity is at a single moment. That's why we need the derivative. And speaking of the derivative, here are some derivative ideas we reviewed. Acceleration positive, the function whose derivative is acceleration, namely the velocity is increasing. If the acceleration is negative, the function whose derivative is acceleration is decreasing. In order for the particle to change direction, the velocity must change sign. And then we actually started talking about this, but never finished talking about that because I wanted to connect things back together for you. So what we did was we took our function from the interval 0 to 6 and we plotted our position by substituting the values of t into here, and we plotted these points approximately, and we noticed that somewhere around 3 we got to be going back in the rightward direction because t of 4 was a number bigger than t of 3. So that means we're headed that way. And I observed to you that it doesn't mean you change direction at 3. It could be some other value. It could be close to 3. And we connected this to the idea of looking at the graph. So looking at the graph we did on our calculator. So this is that x of t function. And we did our normal analysis. So we noted where the function was increasing and decreasing. We said that means the derivative is positive and negative, but we are not talking about the derivative of position only. We're talking about velocity, and we're talking about positive velocity, we're moving right. Likewise, the derivative of position, velocity, when negative, you're moving left. And this allows us then to actually talk about what the question was asking. The question was asking for the distance traveled. So how do you do distance traveled? Now, normally, what we're used to is we're used to starting out with displacement. What do I mean by that? A statement like, I traveled 50 miles. That's a statement about displacement. What we're going to be talking about is something more like this. It's about 50 miles. So if you look at this statement right here, these are the types of statements we're actually going to have. So I've got this right here. This is like my t equals 0, right? And this is my t equals 6. Yeah? So how would you figure out how far you traveled? Well, you'd probably want to subtract those distances. Right? That's kind of what you're thinking. That's how you do that. Okay. Well, that actually doesn't work here. In our specific map of our points, that doesn't work. If we do what we just suggested, we get this. We get from 4 to wherever it is 6 is. Way the heck over here. That's what we get. That's not the distance we traveled. Okay, why is that different? Well, because I didn't tell you, oh, I didn't drive right from Oswego to McHenry. I drove to Minooka. Minooka, if you didn't know, is south of Oswego. So I started at Oswego. I drove down here to Minooka, and then I drove back to McHenry. That maps kind of what we came up with, right? So if we're just looking at the starting time location and the stopping time location, there's a lot of crucial information that's left out. We need the other stops to get the distance. To go back to my driving example, if we looked at my odometer would count everything nicely from Oswego to Minooka and then from Minooka to McHenry. If all I did was just look at the distance from Oswego to McHenry, that wouldn't match my actual odometer, would it? No. So in order to do distance, what we need to do is know what those other stops are. And then what we can do is calculate the distance between each stop. And when we get to the second half of the class, which won't be for a couple of months still, this becomes much easier because we have a new technique. But for right now, this is kind of what we're stuck with. We're stuck with calculating all of the stops. And what I mean by stops, in the terms and context we're looking at, is resting points. And when I say resting points, if you go back to all of that vocabulary we talked about, that's when the velocity equals 0. And if I can close and finish up by going back to my example of driving from Oswego to McHenry, but wait, first I went to Minooka, think about what had to happen when I got to Minooka in order to turn around and start driving to McHenry. What did my velocity have to equal in order to turn that car around? My velocity had to equal 0 at some point in time. I mean, you could argue, well, you did a loop and you never actually, okay, well, sure. But in terms of southward direction, which is what velocity means, because remember, velocity is a vector. My southward progress had to be 0 in order for my northward progress to begin. So when you're doing total distance, the thing you're actually doing first is figuring out the stops. And then once you've got the stops, you've got your different chunks, and then you can add up your chunks to make your total distance.